There are 6 Raspberry Pi computers in this little box. Each of these has 4 CPU cores and 8 gigs of RAM, so in total there's 24 cores and 48 gigs of RAM. In full tilt, this thing only uses 40 watts of power. 6 Pis should beat 1 CPU, right? And it ain't cheap. This whole cluster, including 6 2TB NVMe boot SSDs on the bottom, is $2,200. If you want a 24-core PC, you're looking at a 3960X. Admittedly, that's just the CPU, but that's $200 less.
What a savings.
But even if RAM, a motherboard, and all that other stuff doubled the price, which it doesn't, that Threadripper will absolutely destroy the Pi cluster's performance. But that's comparing apples to oranges. What if we could compare apples to apples? Well, for that, I had to take a little field trip.
Is Patrick from STH, and today we're going to talk about an ARM server. Oh wait, it's Jeffy G.
Hey Patrick.
Hey Jeff, how you doing?
I see that you have this awesome looking ARM server behind you.
Yeah, this is an Ampere Ultra Max server. It's awesome.
All right, can I come in and we can talk more about it?
Yeah, totally. Let's do it.
All right, can you tell me about this server?
Yeah, sure. Okay, so this server is actually based on an Ampere Ultra Max M128-30. And that M128-30 means that we have 128 ARM cores. It has a total of 3 gigahertz of clock speed. They, of course, can alter both of those, but this is basically the fastest ARM CPU that you can buy today.
So each of these little compute modules has 4 cores at 1.5 gigahertz, and my cluster has 6. So this thing is at least 10 times faster.
Hopefully.
I noticed there's some other, like, look at all the RAM there. This thing has 8 gigs of RAM.
Yeah, so this system has a total of 512 gigs in it, and there are 8 memory channels, DDR4 3200. You can put up to 2 DIMMs per channel, so you get a total of 16 DIMMs next to the CPU.
And there's a lot of PCI expansion I see here too.
Right. So this has PCIe Gen 4, and this is really designed, by the way, to be a competitor to things like these Intel Xeon, the AMD EPYCs, and so you have tons of PCIe Gen 4 lanes, and you can put things like even GPUs, which we're going to have pretty soon.
And there's, can I take one of these out?
100% you can.
So
3.84 terabyte NVMe SSD.
I think that kind of beats the Pi a little bit with its 1 lane of PCI Express Gen 2.
Yeah, a little bit.
And then there's dual redundant power supplies.
There are 80 plus titanium power supplies. And then we have a bunch of fans back here. And really, this is a form factor that's designed for the edge. So we've taken the risers out. But this is really designed for the edge, so it's shorter depth. And this is the type of thing that if you wanted to go put GPUs for AI inferencing, remote desktops, you want to go put FPGAs for AI inferencing or networking. So like if you have a 5G base station, or you want to go just put high-end networking or something like that, you can totally go do that in the system.
Yeah, and speaking of that, built in, I see there's a couple cages for SFP. What are
so those are SFP 28, so 25 gig Ethernet, which is built in.
And then there's also BMC for
Yep, so this system has a BMC for out-of-band management. And actually, there's a second ARM processor here, which is the ASPEED AST25 or 2600. So that's actually another ARM processor that runs OpenBMC in this system.
So if you put some DPUs in here too, you'd have lots and
lots. Oh yeah,
lots
you could
more.
have many. It'd be like Conception, basically.
And then under here, there was another thing too for networking, right?
Yeah, there's an OCP NIC 3.0 slot here as well. So there's lots of different ways that you can configure this system with risers and different network cards and what have you.
Just as a point of size comparison, here's the Pi cluster with 6 nodes, and it's a little bit smaller. You could probably fit a few of these inside of this box. I think one thing that would be really interesting is to see how these two compare in speed with a cluster benchmark, and that's what I'm going to do. But another thing that's interesting is you can't buy either of these systems from Micro Center, but you can buy just about anything else, and you know what? They're the sponsor of this video. I visit the St. Louis Micro Center all the time to pick up a hard drive, a power supply, or even 3D printer filament. They have everything. Well, except they don't sell the Ampere Ultra Max, at least not yet. But they do sell Supermicro servers, and they even have a maker section that takes me back to my youth when I pick up parts in an electronics store and hack together some cool device. Micro Center has locations all over the US, but if they're not yet in your town, visit them online at microcenter.com. They have an exclusive deal for new customers, $25 off any AMD or Intel CPU. Use the link in my description and get started on your next build today. So who would be deploying these things?
Yeah, so the Ampere Ultra and Ultra Max are really used a lot of times by the cloud providers. So that would be folks like Oracle, I think was the first one to deploy it, but then you also have Microsoft Azure, you have Google Cloud. This is really the response chip to something like the AWS Graviton series. And then folks are looking at, well, how do you take the processors that are currently in the cloud and then also deploy them at the edge for things like 5G and all that kind of stuff. And that's really what this server is for here. This is more of an edge platform designed to have that continuity between clouds and edge.
So one of the things that I want to see, you mentioned edge there, and I know that is one area where sometimes somebody would deploy a Pi cluster because a Pi runs on 5 to 10 watts of power. This thing, 100 watts, 200 watts.
Probably idle in the 120, 130 watt range.
So a little bit more. So edge can mean a lot of different things, and sometimes it's a deployment where there's just solar power or something like that. Other times you have grid power with good backup and all that. So I think that those are things people consider when they have a power budget, a price budget. But what I really want to see, just out of curiosity, is how much faster this is. It seems on specs that it should be 10 times faster, but I want to see how much faster it is than my Pi cluster. So I'm going to test the Pi cluster first, and then we'll run this thing. One thing I like to do on my Pi clusters is run high performance Linpack. That's the benchmark that's used for the top 500 supercomputer list. And at Supercomputing 21, I had a little competition with Patrick. We wanted to see who could build the best ARM cluster in a box. I built this Turing Pi 2 cluster, and it clocked in around 51 gigaflops, good enough to make it on the supercomputer list, at least in the year 2000. But Patrick, well, he showed off an impressive server with a bunch of expensive NVIDIA DPUs with 56 ARM CPU cores, but he didn't run Linpack on it, so I'm going to call that one a tie. So at home, I rebuilt my Pi cluster using this kit called the Super 6C. It comes with almost everything you need to build a supercomputer in a box, except for the Raspberry Pis. Hopefully there'll be more available soon. I mean, even Upton says they will be.
I think in 1 year, hopefully Raspberry Pi will have recovered from the lingering effects of the COVID-19 pandemic.
I built a Ceph storage cluster first, and for that video, I built a network storage cluster with 6 Kioxia XG6 SSDs. But Kioxia reached out and told me those things are old-fashioned now. So they sent me 6 of these. These are the latest XG8 model, and Patrick has a great review of them on the Serve the Home website. Link below. Now, the number one reason people don't think Raspberry Pis are reliable is because they use microSD cards. And for that Ceph storage cluster, I actually was booting them off microSD. But not anymore. The Compute Module 4 boots directly off NVMe SSDs, so I tossed out all the microSD cards this time. The Super 6C board has an M.2 slot wired directly to each Pi. But to make sure I could actually boot off of them, I had to update the Compute Module's firmware, then flash Raspberry Pi OS to each SSD. To update the firmware, I popped each of my Compute Modules into this Pi Tray Mini, plugged it into my computer, then ran the USB boot software from Raspberry Pi. I could actually update the firmware directly through the Super 6C. It's nice that it has these little USB ports, one for each Pi, but I just like the convenience of my little Pi tray. In USB Boot's config, I set up the boot order so that last digit, the 6 there, would force the Raspberry Pi to try NVMe boot first. I have a blog post covering the process in detail, and I'll link to it below. So I flashed all 6 Pis and made sure they did the happy little LED blink thing at the end, then I moved on to flashing the SSDs. For each SSD, I plugged it into this NVMe to USB adapter and plugged that into my Mac. I flashed each one with Raspberry Pi OS and set a host name for each one, like Node 1, Node 2, and so on. I also made sure to mark which was which and put one SSD under each Pi so I could keep track of which slot they go into. I mean, I could have done better than the post-it note, but that was the quickest way to keep track of everything. Now it's time to load up the Super 6C, and I'm really happy DeskPi listened to my feedback from my earlier video. They sent me this updated board after I mentioned the USB header had the wrong pinout and some of the ports were a little off. This new revision is much better and fits perfectly in the official Super 6C ITX case. The case comes with 3 cooling fans, front panel USB, a power and reset button, and it even has some screw holes on the sides that look like they'd be perfect for rack mount ears, but so far they're not selling any. Hopefully that's a thing because you can unscrew the rubber feet and this thing would be great in 1U of rack space. The case also comes with 6 giant heat sinks and all the screws and thermal pads to get it all installed, so enjoy this last bit of assembly. And yes, that's the LTT screwdriver making an appearance again. I'm actually surprised how many times its default bit set has come in handy, especially that 2.5mm hex bit. I'm going to do a follow-up video on the LTT screwdriver now that I've used it a few months, so if you're into that sort of thing, subscribe. One thoughtful addition DeskPi made for this case is this access panel on the bottom so you can easily swap out microSD cards and NVMe drives. It beats having to take out the whole board just to get to the underside. Once I booted the cluster the first time, I noticed the fans are a little bit loud. I was getting over 50 decibels from 6 inches away, but they kept the Pis from throttling it at the base clock speed at least. The ports all line up perfectly now, and I like the fact that the case even includes Wi-Fi antenna mounting holes if you need wireless. For more opinions on the Super 6C board itself, go check out my older video. With everything set up, I wrote an Ansible playbook to manage the cluster and to load in high-performance Linpack. The entire setup is open source, so if you want to replicate my results, go check it out on GitHub. You can even run it on your PC or Mac as long as it can run Linux. The playbook compiles tools like MPI and Atlas from source so they can get the best possible performance. Then it runs the benchmark and spits out the result. And at the base 1.5 GHz clock, there was no throttling at all, even while all 6 Pis were spiking their cores to 100%. After tuning the HPL settings a little, I was able to get 60 gigaflops, and the cluster used about 41 watts of power while it was running the benchmark. I wanted to see how much faster it would be overclocked, so I set all the Pis to boost to 2 GHz and ran it again. This time, power usage was all over the board, spiking up to 64 watts, and the benchmark was taking forever. I looked at the temps and saw the Pis were actually throttling. Apparently those 3 little fans aren't quite enough for a cluster of overclocked Pis running full tilt, so I popped the lid and decided to go for my biggest fan. I pulled out my giant USB Noctua fan, turned it all the way up, and put it on top of the cluster. The temperatures were much better and power was steady this time, about 51 watts. When the benchmark finished, the overclocked Pis mustered a little over 70 gigaflops. So looking at the 2 results, I had 60 gigaflops using 40 watts and 70 at 51 watts. If I divide gigaflops over watts, I get an efficiency of 1.5 gigaflops per watt at base clock and 1.4 overclocked. So that takes care of my cluster. You got this thing back. You ran a bunch of benchmarks. You had a little adventure doing that too. But can you tell me what kind of performance we got?
Yeah, so we ran the exact same script on this system as was run on the Pi cluster. And we are using Atlas tuning and stuff like that to get the best performance we can. And we got around a total of 1 teraflops for about a 500-ish watt power budget.
So that's about two gigaflops per watt.
Yeah, something like that.
More efficient than the Pi cluster.
It is, yeah.
A side note, my M1 Mac Studio got 4 gigaflops per watt. So
there you go.
A little more efficient there. Good job, Apple.
Newer TSMC process as well, I think. Yeah. Is that true?
Yes, yeah.
Yeah.
Can you also tell me a little bit about price too? Because this Pi cluster I mentioned was about $2,200 total. With all this, you don't need all the SSDs that I have in it. You know, what kind of pricing are we talking about?
Yeah, so this is definitely more than like a $5,000 system in most cases. You're probably going to be spending probably closer to 10 on a system that would be similar to this and how you'd actually configure it to go and deploy. You can of course spend. We have one that we're going to be reviewing pretty soon that I showed you that we're going to be that review's coming up, but that will definitely be a much more expensive system. Subscribe
to Serve the Home. You're going to want to see that server.
Yeah, many GPUs, but I think on a price performance perspective, like this is actually pretty darn good compared to a Raspberry Pi cluster at some point.
I mean, what, 13 times more just on that specific benchmark. We're seeing 13 times more performance for maybe 2 to 4 times the price, depending on the configuration.
Right. And you still have things like more networking, more expandability. We can put more storage in it. I mean, there are a lot of things that you get beyond just the compute side that I think you have to take into account as well, especially when we get to these larger nodes.
Like the fact that this has 1 gigabit networking, and you're not going to be able to get too many bits and bytes out of this thing. So we ran Linpack, and that's, the reason I did that is because top 500 list, it's kind of cool to know how your computer ranks in there historically. You guys do a lot more in-depth benchmarking for a server like this than I do usually for the Pis. I'm usually just doing the basics. Talk to me a little bit about benchmarking methodology, why Linpack may or may not be a helpful benchmark to know.
Yeah, so I'll give you a couple of things. So one, on a big chip like this, typically what you do, and you do this on, by the way, the Intel Xeons and AMD EPYC Genoas and all that kind of stuff, you actually would split this chip up into usually like 4 different quadrants. It'd be like NPS equals 4. And what you do when you do that is you actually kind of localize the memory access and kind of localize the data transfer on the chip, and that gives you a little bit better performance. There are other optimizations you can use in terms of math libraries and stuff like that. So we're going to say this is about 1 teraflops using a similar type of build system and scripts that we were using here, but there are some some optimizations that when you see things like the actual top 500 numbers, those are definitely, sometimes we use custom compilers to use all kinds of crazy BIOS settings, all that kind of stuff to get better performance than we would have in something like this.
So this thing, the price performance is pretty good. It's obviously better than the Pi cluster here. If you need the performance, if you don't need it and you're deploying the edge and you have low power budget, that's great. But if we're talking about data centers where these things often would end up, I know that Genoa just launched. How does this compare to a platform like Genoa or Intel or anything like that?
All right, so just kind of taking a look at the chips. This is the Ampere Ultra Max, is 128 ARM cores. This is the Genoa 9654, which is 96 cores and 192 threads.
As a quick size comparison, this is the Raspberry Pi.
Yeah, that kind of gives you some just kind of sense of how big these things are. And these are only the processors, by the way. These do not have things like have all the memory and all that kind of stuff on them. So the key thing here, though, is that you do get a lot more in terms of performance on I/O. So you get more memory bandwidth. You get things like more PCIe lanes, faster PCIe lanes. This is PCIe Gen 5. This is PCIe Gen 4. And then the other side to it is that when we look at things like Linpack, a chip like this will probably do over 5 teraflops, and that's in a little bit higher of a TDP range, but on the other hand, when you actually look at the total system power, it's probably, for a dual socket server with these, it's maybe an extra, 10-20% performance when you're running Linpack versus running like 2 of these systems, and you're getting way more performance. You're getting like 10x the performance, right? So I would personally take 10 to 20% more power consumption for more performance. So people say, by the way, that ARM is always more power efficient than x86. That's not always the case, because this is optimized for not just things like serving web pages, but also things like these HPC applications. Whereas the Ampere Ultra Max is really designed more for things like you doing Nginx web servers or stuff like that. So this is really focused on integer performance. This is integer and floating point performance.
And so we're talking about 2 gigaflops per watt, maybe a little more than that for these CPUs. But when I talked to you about this before I started this whole project, you mentioned that GPUs are well beyond that.
Yeah, and so if we look at things like a CPU like this, you might get something like 10 or so gigaflops per watt. And then, if you look at a GPU, you might see something like, 40, or depending on the GPU and stuff. So just kind of like when you go up this scale, right, you might get like 1 to 4 for a desktop CPU. For a high-end server CPU, maybe you're going to get 10. And then when you get to GPUs, you start getting to 4. So one of the big things that you see in the industry is using these Ampere Ultra Max processors with high-end GPUs to augment the floating point performance. And we actually did a video on that with the Gigabyte system. And we did the A100s plus this Ultra Max GPU.
So your workload has to support that, though. So not everybody's workload can just go over to GPUs.
Right, and not everybody wants to go put $10,000+ GPUs into a server just to save a couple bucks on a CPU.
So you mentioned that when you got the top 500 benchmark result, when we ran Linpack, you actually had a little bit of an adventure getting it running. And that's something that I see it as a theme. The Raspberry Pi, this compute module, has a processor that's well supported by the Raspberry Pi group themselves. So when I want to get an OS, I usually use Raspberry Pi OS. But I found that with a lot of other SBCs that use ARM CPUs, often you have to rely on an old Linux kernel or support for something, and it's not documented that well, and it's kind of all over the board. How is it in the server space, especially with this chip?
So I'll definitely tell you that we started doing ARM server CPU reviews, especially in the data center, around the Cavium ThunderX days in like 2016, and back then, especially before Ubuntu 26 or 16.04, it was absolutely, the world was terrible for ARM servers. Over the years, it's definitely gotten a lot better. And at this point, we actually just downloaded a Ubuntu image, installed it on here, and it generally worked. We have a little bit more of challenges when things happen, like we actually had some disk corruption. I don't really know why, but just we turned the system off and then on, put it in the studio over here, and then the OS image was corrupt, so we had to reinstall it, and then OpenBMC didn't want to install it, and so we had to go and just put a little USB drive in there, and that finally fixed it. But just like little things like that, you wouldn't typically see, and even in like things like the newer, the Genoa systems or the Sapphire Rapid systems, which are still technically pre-production, you definitely can tell that there is some difference between the maturity of an x86 server and an ARM server, but it's way closer than it used to be. These are deployable at this point, so I wouldn't say that they're totally funky, just science experiments or anything like that. But there is still a platform difference if you want to go and deploy bare metal.
So the 128 core Ampere server might cost 3 times as much, but it's way faster and more power efficient. And that's before we even talk about dual 25 gigabit Ethernet, 128 lanes of PCI Express Gen 4, and all the other nice things Supermicro stuffed in this box. But that leads to the question, who is this Pi cluster for? Well, the market for something like this is small, especially with Pis being so hard to get right now. But there are other CM4 compatible computers you could put on here, so I might test a few soon. But even with faster little ARM CPUs, the performance won't be anywhere near what you can get with a real cloud server. But it's still fun for experiments and could be useful in some edge use cases, like if you have limited power. I want to thank Patrick from Serve the Home for letting me come out here and take a look at this new server, and I especially like STH's new Mini PC series, where they walk you through some of these awesome little fanless PCs you can use to build a custom router at home. So go subscribe to STH both on their YouTube and their website, and there are links below. Until next time, I'm Jeff Geerling.